All right, so today we're going to be talking about Introduction to Linear Regression. Super excited about this because we're finally getting into modeling. One thing that I'm not sure if I'd mentioned, I don't know if I've ever mentioned Jupyter Notebook extensions. As we move to like doing bigger projects and like working with longer notebooks, highly recommend getting Jupyter Notebook extensions. That's what's allowing me to have this like table of contents on the side. And what this table of contents does is it like automatically looks up like, you know, the different size of our markdown headers and creates this table of contents for us. Other fun extensions you can have. So once you download Notebook extension, I'll send out a link to the Slack later. Let's see, I use collapsible headings. Collapsible headings is a great one. So I like to like collapse sections like this. Well, these don't really, let me see a good example. So for here, if I have a lot of like code cells here, I can collapse this and it'll just make things a little neater so I don't have to scroll like through the entire notebook. Other things, let's see, table of contents, collapsible heading. There's one that you can actually like split your cells so you can have like half a cell on each side. But this is a fun thing to look into. Definitely as you're starting to use notebooks for bigger projects, highly recommend just like exploring these. And I'll send out a link to like how you can download this. Super simple, like 2 lines in Terminal. All right, linear regression. So linear regression is our very, very first model. And for all of the models that we're working with, they are based off of the statistical learning theory. And the main idea of statistical learning theory is to construct a model to draw certain conclusions from the data and then be able to use this model to make predictions. So for our project, if anyone has looked into it, is a housing price data set where basically you want to use different features of houses, like how many bedrooms, bathrooms, how many square feet, number of floors, to predict the price of a house. And so what we would do for this project is create a linear regression model that can predict housing price in terms of these features. And then we're going to use this model to be able to make predictions. So in the future, let's say you have a house that's like 4 bed, 3 bath, I don't know, 2,000 square feet, what that house would be priced. So that's the goal of the rest of this mod. So before we get into like linear regression specifically, some very important terminology that this part isn't really included in the Learn Labs. It's actually another pretty common interview question. What is a model and what is an algorithm? Sometimes they can be used interchangeably, but I think it's important to like really hammer down the proper definitions for each. So you might have heard the phrase training a model. And a model basically trains via its algorithm. And you can think of an algorithm as a series of steps that a model takes to train. So while the best model for your data is a regression that has an equation in this form, and I'll talk more about this part later, the algorithm is the process of choosing the right values for your parameters beta 0 and beta 1. So this is basically what our linear regression model looks like. So any linear regression model follows this format, where you have a bunch of beta parameters and x's. So here, y is your predicted value, x's are your variables, and betas are your parameters. So in the case of like housing prices, y, the price of a house, can be expressed as an equation of some parameters, some constant value, plus some other parameter multiplied by, for example, number of square feet. So the idea of performing a linear regression is you're going to get the best values of betas such that this model, this equation, will predict the housing prices as well as you can. Cool. So that's what a model and that's what an algorithm is. So the algorithm kind of trains the model. All right, really quickly, let's talk about data. So in the context of statistical learning, there's 2 main types of data, dependent and independent variables. There are a bunch of different definitions for this, but usually our dependent variable is the target, what we want to predict. And so for our project, our target variable, our dependent variable is the price of a house. Independent variables are all the other variables that you're using to predict the price of the house. So predictor variables, input variables, features is a very common word that I use as well. And so there's just these two types of variables that we're using here. So just remember, we're using independent to predict dependent.
Yes, real quick. So just clear. So historical pricing data can be independent variables, right?
Actually, yeah. Let's say you want to predict the price of a house right now. We can take a look at its previous price. Yeah, for sure.
For sure. Okay, just wanted to make sure. All right.
That's a good question. That's actually more of time series analysis, which is a mod 4 topic. And you'll see there are reasons why we typically don't want to use past data in a linear regression, but we won't get too into that for now. So in this example, we have predicting annual income based on age. So in this example, we want to see that. And here's just a scatter plot showing age and annual income. So when you see a scatter plot that kind of looks like you can sort of fit a straight line in, that's a good indication that you will want to use a linear regression. And so this statistical model, linear regression, defines this relationship between the dependent and the independent variable. So what you see here, relationship between age and income can be shown using a straight line connecting all the individual observations in the data. So this line is our model. If anyone has done, like, I don't know what this would be called. Is it geometry? No. Algebra? Functions? I don't know. But if you remember seeing the equation of a straight line, I think you might have seen it in the form y equals to mx plus b or mx plus c. This is basically the same thing. This first beta 0, the one without the x, is the intercept. And then this other beta is the slope of your curve, of your line, sorry. So every linear regression looks like this. Why it's called a linear regression is because this is actually a linear equation. It's just that each of these increasing beta or increasing beta 1 will have a linear effect on y. And we'll get more into that as we get to multiple regression. And actually, no, we'll get into that later when we look at the output of our linear regression. So basically, every line has this formula. And the idea is we want to choose the best beta 0 and beta 1 to create the line that fits this data the best. Cool? Any questions so far? Awesome. And these betas are known as parameters or coefficients. Typically, in a more general sense, they're called parameters, but specifically for a linear regression, they're called coefficients. All right, so how do we choose the best fit line? How do we know what line is the best? How do we know what combination of intercept and slope will fit our data the best way? So there is this idea of a cost function, and I talk about cost function here. So every model that we're going to talk about throughout this course has an associated cost function that its algorithm uses to learn the best parameters. So in this case, for a linear regression has some cost function that the algorithm will use to determine the best betas, the best intercept and slope for this data. And the cost function that's used here is least squares. It's called the least squared error. And basically what least squared error is the algorithm will look for the line that creates the least amount of distance between the points and the line. And just because there's positive and negative error, you just square the error to find so that it'll always be positive. So basically, what the algorithm does is it calculates a bunch of distances between every single data point and the line, finds out what that error value is, and then constantly shifts the the beta zeros and beta ones until it finds a good or a best fitting line. Cool. There are many different ways this can be done. You might come across methods that use like matrix multiplication, which we'll actually talk about when we get to linear algebra in mod 3. Using covariances, I think in the labs you're asked to calculate this using covariance if I'm not wrong, or you can do it using gradient descent. I think if anyone did the bootcamp prep, you actually solve this using gradient descent, where you start at some like flat line and you slowly improve your line with using iterations. And it'll basically look for your cost function, which is the total errors, and try to get that as low as possible. Questions so far? So yeah, so these are basically sum of squared residuals, which is the same thing as the squared errors, which is basically the model's prediction, which is basically, let's say this point here, the model would have predicted it to be here, where the line touches. So you're just taking the distance between y hat, which is this point here, and y itself, each point, squaring this amount, and doing the same for every single point here, summing it together. And we want to make this as small as possible. So that's the cost function for a linear regression. Cool? All right. So once your cost function is at its minimum, and for a linear regression, there is an absolute minimum. So there is a way to find the best fit line. Once you have that, you also have to talk about how well fit is your best fit, right? Because there's no way we can get our line to perfectly pass through every single point unless all your points are perfectly along the line. And so there's this other metric to determine how well the line fits our data, and that is the coefficient of determination, or R squared for short. And what the R squared is doing, it is basically comparing your line to a baseline model. So anyone know what the idea of a baseline is? Any ideas? So imagine like I'm training for a 5K. I've never run in my life. And I like just run my very first 5K. I get like a time of like an hour. That will be my baseline time. And then as I train and as I improve, I will basically compare my new and better times to my baseline. And so I have like a really sucky timing, and over time I get better. So in this case, we're comparing the fit of your line to a baseline model. And the baseline model here is a flat horizontal line. So this diagram is a little bit confusing, but I'll put this in frame with this equation here. We're taking the proportion of your sum squared errors. So if this gray line is our model, we're going to do the same thing that we did for our least squared. We're just going to take the squared distances between the point and the line and sum that up here. This will be the numerator up here. Next, what we'll do is we'll do the same thing, but we're going to compare it instead to the line. We're going to compare it to taking the distance from each point to this baseline. And where this baseline is, this will just be the average of y. So whatever this variable is, all of these points, whatever the average y value is this orange line. And what this sum squared total is just the sum of the squared distances between every single point and the flat horizontal line. So obviously, well, actually not always the case, but in very many cases, the distances between your points and the horizontal line is going to be much greater than your distances and this best fit line, because your best fit line was trained to fit the data better. And so you'll get this ratio in the end.
One quick question, Yash. So the baseline, isn't it the mean line?
Yes, the baseline is exactly the mean line.
It's actually the mean line, right? Okay.
It is, yeah.
Yeah. I got confused with that. So I thought it's a different line. Okay.
Awesome. Yeah. The baseline is the mean line.
Okay.
And then you'll just take 1 minus that, and you'll get a value between 0 and 1. And so an R-squared value basically tells you how well your model is fitting the data. This is an interpretation that I expect to see in your projects. An R-squared value of, say, 0.85 can be described conceptually as 85% of the variations in the dependent variable y are explained by the independent variable in our model. Does that sentence make sense? It's saying that, let's just talk about this data. Having this line here explains 85% of the deviations of our points. That's kind of what it means.
The R2 has to be 0.85.
Well, the R squared is something that is derived from our model. So we get our R squared from our model. So there's actually no, I mean, of course, the higher your R squared, the better your line is fitting the model. And so this is just some arbitrary number. But whatever R squared value you get, it is the percentage of variations in your dependent variable y that are explained by the independent variable in your model.
Now, Yish, I mean, I'm not sure if it happened, if we get into this in the future, but is there also with linear regression, having that hypothesis as far as what you want your confidence interval, to be or something like that? Okay.
Absolutely. We're actually going to get into our hypotheses.
Okay.
Right after this.
Okay. Sounds good.
Yeah, right after this. All right. So these are the first few things. Oh, actually, before I move on from R squared, something I want you guys to think about. If your R squared is high, does that necessarily mean that it's a good model for predicting other data? Just think about that. I don't need an answer now, but just think about, is getting like a 99% R squared a good thing for making predictions? Just think about that. I think I'll come back to this on Thursday. All right, so let's do our very first regression. We'll start with simple linear regression. So you'll see that the next section is actually called multiple linear regression. We're just using one variable to predict one variable. So it's called a simple linear regression, where we're using one independent variable to predict our dependent variable. So these are the things we're importing. We have, as usual, pandas, stats models, which is the library that has our regression. OLS stands for ordinary least squared, which is least squared comes from the algorithm that we were talking about earlier, the cost function we were talking about earlier. Matplotlib for some visualizations, and we'll style it Seaborn. So I took this, oh no, it's not here. Hold on, I must have deleted it. Let me move this back, height and weight, CSV.
So this simple linear regression is always 1:1, one independent to one dependent?
Yes, that's correct.
Okay.
All right, let me copy this real quick. Now I'll paste it back on my desktop. All right, let's see if this works. Cool, awesome. So this is our data. We just have height and weight. And in this case, I want to predict weight using height. So just to start, let's just plot it on a graph. Always good to do a little bit of EDA. And this is what it looks like. As you can see, it sort of looks like a straight line will fit very, very well. So it does seem that height and weight are quite correlated and are quite linearly related as well. Now, I did talk about this setting up a little bit when we were talking about ANOVA, because ANOVA has the same setup. But basically, the way that OLS takes in your formula, or like just takes in the information to do a regression, uses this syntax. It's kind of annoying because it's all in a string. You might have to end up doing string formatting for your multiple linear regression, but this is actually the language R. So if anyone has heard of the language R, that's what it looks like. So we define our formula first as a string, and then we create this model object where we tell it we're using OLS, giving it the formula, giving it the data, and you always have to call .fit. So the .fit is what is fitting the line to your points. And then the output, to get an output, you do model.summary. So if we don't do model.summary first, I don't think you get any output. Yeah, there's no output. But we do that. And here's our first OLS summary. Whenever you do model.summary, after you fit a model to any data, you're gonna get this output. And there's a lot going on here. I actually copied this from one of the labs. One of the labs actually goes through every single piece of this output. But I wanna just talk about the important ones that we're gonna need to interpret. So first, on the left side of the first table is just a bunch of summary stats about the model that you used. So our dependent variable here was weight. We're using the OLS models, least squares method. All of this date time, not important. How many observations we have, df of residuals, so degrees of freedom. So the number of degrees of freedom is always n minus the number of parameters. So because here we have beta 0 and beta 1, we have 2 parameters, which is why the degrees of freedom of residuals is 20 minus 2, which is 18. Degrees of freedom of models, I honestly don't remember what that is off the top of my head. Actually, let's take a look. Degrees of freedom for the model is the number of parameters in the model, not including the constant of intercept term. And this is the intercept term. All right, so here are the more important ones. R squared. You can see that we have an R squared of 0.955. That just means that this model can account for 95 or closer to 96% of the variance in our weight variable. Adjusted R squared. Adjusted R squared is something, I think that there's a lab on it, but basically adjusted R squared takes into account the number of variables that you have. So when you get to multiple regression, when you have not just height, but maybe you have like, I don't know, other variables like blood pressure or like iron, I don't know. If you have other things that you're trying to use to determine weight, basically you'll see that if you have more features, R squared will always go up. And so to like normalize that, adjusted R squared, if you have a lot of features, adjusted R squared might be a better thing to look out for. And it basically means the same thing. You're just accounting for the number of features.
Is it often just close together, or is a lot of
these values? In this case, it's close together because we only have one other variable that we're looking at. If we're looking at way more variables, there will be more of a deviation.
Okay.
Mm-hmm. I heard another question.
Yeah, I was asking. So now these are the R square is based on 3 decimal places now in this. So does that mean that like we have the volume of the data is around that 1,000 mark?
Definitely not. So R squared, as you remember, it is a ratio of squared differences. So the number of data points we have here is only 20. Okay. There's a lab on like deriving R squared, so you'll see that yeah, it can be pretty much any decimal point because it's taking a fraction of residuals.
Okay.
But I personally don't really remember the R squared formula off the top of my head. I think a good thing to remember is just what the definition is. Like if you can say this just is the amount of variation that is explained, as long as you can do that, I think you're good. Cool. So R squared, very, very important ones. F statistic, does anyone remember where we maybe briefly talked about F statistic? Anyone? We actually talked about F statistic and ANOVA. But for this, we don't typically talk about F statistic. Just curious if anyone remembered. So main thing for this top table is really just R squared and adjusted R squared. The next important thing to look at is this table. Actually, in this table, almost everything is important. So here we have our intercept term, which is our beta 0. And here we have our height variable. First thing, we have our coefficients. So coefficient of intercept, meaning that beta 0 is negative 204. And beta 1, which is the variable that we multiply, which is the parameter that we multiply by our height, is 5.539. What this means is that every 1 inch increase in height will lead to a 5.539 increase in weight in pounds. That's how you would interpret this coefficient. Of course, you have to check on the units of measurement. Here, I'm only guessing that weight is in pounds. Yeah, it should be pounds. Weight in pounds and height is in inches. But this basically means that on average, when you increase height by 1 inch, so 1 inch is like half of this unit here. So from 60 to 61, on average, your weight will go up by about 5 pounds. And you can sort of see it kind of checks out. Going from 60 to 61, if you imagine a line here, let me see if I can annotate a line here. So you roughly put a line through here. From 60 to 61, like that. This is about 5.5, not very accurate, but you can see it's kind of around 5. So that's what that coefficient means.
Yes. So, okay. So I have a question about this. So, this would depend somewhat, if not completely, on the, how do you say that? The number of spaces in between each plot, right? So if there were like, is it always matched up? Like, for example, if you want to plot height, you know, 1 inch, 2 inch, 3 inches, 4 inches, 5 inches, or whatever,
yeah.
Right? Does the OLS table always match up to say, okay, for every increase in inch, does that always match up with the actual visualization?
Okay, so it does not. So the OLS output, the coefficient, let me just clear these. This OLS output is always for a 1 unit increase in height. In whatever this variable is, it's always a 1 unit increase in height will lead to a 5.539 increase of whatever unit this is.
Got it. Okay.
So it really does matter the scale of your variable. So if you have like, let's say you're doing your height in inches, but you put your weight in like, I don't know, milligrams for some reason, you're going to end up with a huge coefficient here because 1 inch increase in height is going to lead to like, I don't know, like a few thousand milligrams increase in weight. So it does depend on the scale of the variables that you're putting in.
So then, I mean, probably then if you see a crazy number like that, then you could probably go back and change the way it's measured and so you can get better numbers. Okay.
Absolutely, absolutely. Like in housing prices, you're going to see that your housing prices are probably around like the 6-figure number. And maybe one of your variables is number of bedrooms. Maybe increasing 1 bedroom will raise your housing price by like 100 grand. However, if you decide to do some data cleaning and change your units of price from just like dollars to maybe millions, instead of the increase being 100,000, instead of this coefficient being 100,000, it would be 0.1.
Right. Gotcha.
So you're always interpreting your coefficient in context of the variable.
And that's for every single one of those variables.
That's right.
Gotcha.
That's right.
Okay.
The intercept, a little bit more vague, but the intercept is basically saying that if your height is at 0, what am I trying to say? The intercept term, is basically saying that if your height is at 0, your weight is at negative 204. What's that saying is, I wonder how do you...
that's the y-intercept.
Exactly. How do you change the graph such that it shows the full... I'm gonna have to look this up.
I also wanted to ask you that do we have to manually draw the line? No, right?
No. There's actually, if you use Seaborn, there is a there's a regression line function.
Yeah, I mean, I remember that because I used it in the previous project.
Yep.
But I just wanted to know with linear regression, it changes or not. No, okay.
Yeah. I'm gonna see, let's see if I know how to do this. This is how you do it, 0 and 200. There we go. And if I do X limit 0 to 75. All right, so with everything at 0, this is what our points look like. Basically, this intercept means that from our best fit line of whatever this is, it will cross this 0 point at negative 204. That's what an intercept is. A little more conceptual, like abstract, but yeah, just because you can't have negative weight. All right, so that is that. Next thing, standard error. Because this is still some sort of statistical test, there is some standard error here. So the next things we're going to talk about are the statistics, the p-value, and the confidence interval. If you remember, we see p-values and statistics when we're doing some sort of hypothesis testing. I think I have the hypotheses here somewhere. All right, hypothesis testing and regression. These are what our hypotheses are. And our hypothesis testing is done for each variable individually. So the null hypothesis is that there is no relationship between the independent variable and the dependent variable. So having no relationship between the dependent variable and independent variable means that the coefficient here is 0, is equal to 0. The alternative hypothesis, conversely, is there is some relationship between the independent variable and the dependent variable. And the idea of a regression is because we want to be able to predict weight using height, we need there to be some relationship between weight and height. The relationship being that, you know, with every increase of 1 inch in height, you get a 5.5 increase in weight in pounds. That's the relationship that we're looking for. And so that's what all of these statistics are talking about. So basically, a p-value of 0 is saying that there is 0% chance that there is no relationship between height and weight. Cool. And for intercept, honestly, I'm not 100% sure how to interpret the p-values in the hypothesis for intercept term, but for the most part, you will only be asked to do it for each variable.
But then this p-value, is it automated?
Yes, they automatically calculate it for you. So sometimes you'll see higher p-values, and I'll maybe pull up an example later. So ideally, because you want there to be some relationship between your variables, right? So because you want a relationship, you want to reject your null hypothesis. And therefore, do we remember what's better to reject the null hypothesis? Are we looking for low or high p-values?
I mean, if you have to, I mean, lower p-value is always better, right?
Yes, exactly. So having p-values of 0 is great. It means that we can pretty much confirm that there is a relationship between height and weight. Let me just quickly see if there's anything else. Oh, and these are the confidence intervals, just like intervals for which contain this value. Can be used to in some interpretation, but not too much. But at least you know what the intervals are. Cool. There's a bunch of other stuff here. All of this is on the labs, but less important to know for now. The main things are definitely the R-squared, adjusted R-squared, coefficients, p-values. And that's it. Any questions on any of these important outputs?
Just one about the adjusted R-square. So that again is right, an automated calculation that happens,
Yep.
or like it's based on our input, which happen. I mean, where we calculate the R square and then.
Yeah, everything on this table is automated. Once you fit your data with OLS, all of this is being calculated for you. That's why I think when you do your project and you run these models, it might take a little bit of time because it's doing all these calculations for us. Yeah, all of these are automatically generated.
My system anyway is slow, so then it go further.
yeah, unfortunately I was the same. Like when I was doing like my final project, I like had to leave my computer for like 7 hours one time. But yeah, that's something to get used to. So yeah, all of these are here. They're also on the labs. I just put them here just in case anyone refers to this. All right, so I kind of went through this already, but let's just talk through it again. P-value is a level of statistical significance. The p-value represents the probability of observing your results given that the null hypothesis is true. So therefore, p-values associated with coefficients as coefficient estimates indicate the probability of observing the coefficient given that the null hypothesis is true. This is just a roundabout way of saying what we already know. Small p-values indicate that coefficients are statistically significant. So as Kishore mentioned, we want small p-values. Cool. Yeah, all of this we already went through. Okay, so we've already run our regression. Now to end off this, there are some important assumptions for linear regression. So you can't just run a regression on everything that you see. I mean, you can, but sometimes, you know, things might not have the right relationship for linear regression. Like for example, if your scatter plot doesn't look like you can fit a line through it, why would you run a regression? So there are some assumptions for linear regression. It is a parametric technique, which means that it uses parameters learned from the data. So therefore, there are some assumptions. And it is kind of mandatory that the underlying data fulfills these assumptions. So as a good practice, you should check for these assumptions that I'm going to talk about. And there are three main ones I'm going to talk about when you're running your regression to see that, you know, was using a regression model for this data a valid choice. So the first one, pretty simple, linearity. Linearity requires that there's a linear relationship between response variables and predictors. So basically between your independent and dependent variables. All you have to check for these is plot scatter plots. Let's see if I can get some examples of scatter plots. All right, so we have some scatter plots here. Something like, let's see if we can get a better photo. Perfect. All right. Having a scatter plot that looks like this is a pretty good sign that they're going to be linearly related. Something like this, kind of. Something like these bottom two, quite unlikely. Two ways that you can do to check for this. One, literally plot the scatter plot and eyeball it. Or two, you can do the correlation coefficient. Something that you can do if you have a lot of variables, which we'll talk about on Thursday. Let me see if I can make a cell here. Is let's take a look at our data frame. Our data frame looks like this. There is a function called built into pandas called correlation. So df.core is one that I use a lot. df.core will basically show you the correlation between every variable with every other variable. So here, since we only have two, obviously correlation between a variable and itself, so height and weight are both 1. But the correlation between weight and height, 0.97. So usually what you would do if you have a lot of variables in your data, just plot a correlation plot, because sometimes scatter plots take up a lot of space. Plot a correlation plot and then choose a cutoff. Depending on what your data looks like, typically I would choose maybe a cutoff, like anything that is less correlated, less than like a 0.7 correlation, I would just take out one of the variables.
So can this be run with two columns? I will now, let's say from the data frame, we just pick two columns and then say, find the
Yep.
correlation.
Yep. You can do df and you can like pick up like height and weight. So imagine if this had more columns, you can do a subset of it and then run.core. It's the same thing.
Okay.
So this will work if it's just like one, but it will just.
So that
one.
now that, so if we want to find the correlation between, let's say the sea facing place, or I mean the waterfront, which is there in the data, right? Between waterfront and the, let's say the size of the apartment, right? If we do just for both of them, so we probably know that, okay, what is the size, average size that is coming up in the apartment, and then like whether there is any kind of relationship.
Yeah. So this kind of alludes to something that's more relevant later when we do multiple regression. Right now, we're just talking about one variable regression. So for one variable regression, you just have to make sure that, you know, your dependent and independent are somewhat correlated. In multiple regression, you have to make sure that each variable, each independent variable is somewhat correlated with your dependent variable. So each of your x's is somewhat correlated with your y. Each of your features is somewhat correlated with your target. And later we'll get into, I kind of alluded to it already, but if you have features that are correlated with each other, you usually want to take one of those out, but that's more for Thursday. So that's the first assumption, linearity, the relationship between your y and any predictor x, and can be tested with scatter plots. This is another good place to look at data cleaning because you want to check for outliers in this case. It's important to check for outliers because imagine if you have an outlier where typically if you have, because we have this outlier here, you see how this line kind of slants up, but without this outlier, the line would fit the points a lot better. So in this case, you might want to look for outliers per feature in a scatter plot. Cool. So yeah, the outlier prohibits the model to estimate the true relationship by introducing a bias, because that one point up there is pulling your line all the way up. All right, so linearity was our very first assumption. Our second assumption is normality. So normality assumption states that model residuals should follow a normal distribution. So model residuals means that, let me scroll back up to the graph here, is that each of these distances, if you were to take these absolute distances and plot them in a histogram, they should look like they're normally distributed. And what we can do to check that is that stats models has built in something called a QQ plot. A QQ plot it stands for a quantile to quantile plot. So if you're plotting your residuals, hopefully it should look something like this, not something like this. So
one quick question. So now when we know that the central limit theorem speaks that, like, okay, if you just pull up, anyway it is going to show as a normal distribution when you're just pulling up mean. So here it's not about the mean, here it is about the actual distribution has to be normal, correct?
Yep, because central limit theorem, we're pulling a bunch of different samples and taking their mean. Here we are literally just looking at the data that we're putting our line to. And we're just looking at the amount that our data, that our prediction is away from our actual points. And we're literally just taking that difference and plotting that into a histogram.
Okay.
Yeah. And so what a QQ plot is, it's actually kind of similar to our Kolmogorov-Smirnov test, where it compares the distribution of our residuals to a normal distribution. To be honest, these shapes are things that I don't really remember myself. Usually I would plot a QQ plot as long as it like lies along the line. I would say, all right, that's pretty normal. If I have a QQ plot that looks somewhat different, I usually actually look it up and see like what this QQ plot means. So this one is basically saying, all right, if I have a QQ plot that like the ends are sort of deviating away, you have a data that's too peaked in the middle. If you have skewed, it will look like that. If skewed the other way, it will go, it would be a flipped curve like that. So QQ plots are something that you plot after doing your after plotting your model, just because it's taking the residuals, and you can't get residuals without first fitting a model. So yeah, you can also do the same thing with the KS test that we talked about before. But this QQ test, I think, is a little bit easier because it is built into stats models as well. So this is basically how you plot it. You can assign all of the residuals to a variable, and it actually takes the residuals from your model. And remember, our model is something that we fit up here. Model is something that we fit up here. So here we have model.summary. Our residuals we can get by doing model.resid. So that is back here, model.resid. And actually, if we take a look, residuals, oops, I haven't run this yet. Model.residuals gives us all the deviation between our data points and the line. So these are residuals, and here, stats models has a graphics folder where you can plot the QQ plot. And so this is what the QQ plot is. And this looks kind of okay, honestly. Like, it's kind of close to the line and good enough, I think. Questions on this? Cool. The last thing we want to look for is homoscedasticity. So scedasticity means variance. So homoscedasticity means that we want an equal variance across your data.
Is there a nickname for this?
Nope. I practiced a lot to say this right. So homoscedasticity is something like this, where if you were to just plot your data points, you want the variance to be pretty equal. And there are ways to check that. I'll show you later. And the opposite of homoscedasticity is heteroskedasticity, where if you have unequal variance, it would look sort of like this when you plot your graphs. So scatterplot is a good way to check for homoscedasticity. Really quickly, you can see here, stats models has again built in exogenous things. Let's see, and this gives us 4 different graphs. So the one that I mainly look for is this, residuals versus height. Is basically for each data point, what was the residual like? And for homoscedasticity, you just want to make sure that this is not like bigger or smaller in any direction. Here, just because we only have 20 points, is kind of hard to say, but ideally you can see that like most of the points are kind of like between negative and positive, like 7.5. And that's not too bad. Ideally, we'll be working with like hundreds and hundreds of data points, so a pattern will start to emerge, like whether it's something like this or something like this. But yeah, there are these other plots, partial regression plots and CCPR plots. These will get more valid and more relevant to us when we get to multiple regression, when we deal with more variables later on. Cool, but that's about it. This is like a crash course introduction to linear regression. Does anyone have any overall questions about stuff we've talked about so far?
So looking, oh, sorry.
Mm-hmm.
Yeah, you can go ahead.
Thank you. So looking at the homoscedasticity plot,
Mm-hmm.
like for the residuals versus height, I just want to make sure I'm understanding. So we're not necessarily looking for like a mirror image across like that horizontal line. We're more just like looking at sort of where's the max height and the min height, because it doesn't really matter along like where it is along the x-axis.
Yes, exactly right. So
okay.
An idea of like what heteroskedastic plug would look like is, let's say like on this end for like the shorter people, we have like smaller residuals. So let's say we like on this end only between like plus minus 0.25. And then on this end, we get much bigger differences. And so that would be a sign of heteroskedasticity. In this case, because on like the lower end and the higher end, we're looking at like pretty much the same sort of differences up and down. So yeah, I would say this is like pretty homoscedastic, but also this is only 20 data points.
Yeah. Okay, cool. Thank you.
You're welcome. Anything else? I think Kishore about to say something.
Yeah, so I actually wanted to have more clarity on the models where generalization or validation and the loss.
Ooh, okay.
Yeah, so the thing is, I mean, I overview, I could understand it.
Yeah.
But then I wanted to have a bit of clarity so that it becomes fixed in the mind. You know?
Yeah, of course. I was actually going to talk about this on Thursday, but I think it's a good thing to at least introduce now. So talking about how well does our model generalize and how well does our model work on like basically the idea of validation. Later when we get to multiple regression, we're going to see that typically when we're building a model, let's say we have 100 data points. We're not going to train our data on all 100 data points. We're actually going to train our data on 80 data points and then test our model with 20 data points. This whole idea of doing like a train test split where you have like a set of training data and a testing or validation data, it kind of works to make our model more generalizable. So basically, if I were to train all, let me pick up an example. Let's use this one. Let's make it a little clear. So let's say I build this model to predict weight using height. If I have this line over here, let's see. If this is our model over here, and so like whatever your height is, let's say like I'm 70 inches tall, my predicted weight would be, I don't know, 185 pounds. Right, that's what the model says. The idea of having that train test split basically lends to having our model generalize better. So for example, let's imagine that this population happens to be like a very specific population of, maybe this is only women. And so if these data points are only women, would this model work for predicting the height of men? Probably not. I don't know how like weight and height works for different genders, but we can guess that probably if we had like a scatter plot of women's weight and height and men's weight and height, the lines would look slightly different. So the idea of being able to generalize is we want to make our model work for any unseen data. So let's say we didn't have, maybe we didn't have any of these points up here. So let's say we don't have any of these. So let's pretend that all of these points don't exist. So if those points don't exist, let me change this line. If those points don't exist, our line actually would look something like this, right? Not very different, but still quite different. Sorry. There's what our line would look like if those upper points didn't exist. So we want to do a train test split to make sure that our model is somewhat sensitive to unseen data. So if we had this line here and we wanted to test our model with these upper points here, we'll see a lot of error on this end. Even though your R squared for these lines in the front on the lower end might be very high, these points still have a large error. Does that kind of bring things together? I didn't plan to talk about this time, so I understand it's a little all over the place. But did that help?
Yeah, it helps a bit. But then like maybe on Thursday we can talk in details on that.
Yeah, Yeah, basically you want to make your model somewhat sensitive to unseen data. So by doing
just one clarity. So like if we are going to do, is it 80-20 better or 70-30 better for training and test?
It's really up to you. I mostly use 80-20, but there's actually not a huge difference on like what split you choose to do. Basically what I was getting at earlier when I asked you guys, is a high R squared always a good thing? Is not always a good thing. So having a high R squared means that your model fits the data really well. It fits the data really well, but it doesn't really say anything about how well it works to predict unseen data points. Because the idea of building a model is to not predict on data points that you already have, but is to predict on data points that you don't yet have. So I know I've drawn a lot of lines here, but basically I hope that what comes across is that even though the model fits this first section really well, it doesn't fit this section really well. So that's why sometimes you want to allow a little bit of give in your R squared so that it will fit other points better. But yeah, we'll get way more into this on Thursday. But cool, we're right at 7 o'clock. Does anyone have any final questions?
Yeah, this notebook is available for download now, right?
Yeah, I'm pretty sure I have it up on GitHub.
Okay.
Awesome. Well, in that case, have a good evening, everyone. I think now it's like come to the time where like we get our sunset right at this study group time, so we have this lighting change, which we will get used to. But everybody have a good rest of your week. I'll see you all at your 101s, and if not, on Thursday.
Perfect.
Bye.